Okay, in part two, we're going to look at word problems. I'm going to do one example, and then I'm going to suggest that you try a second example. I am going to record the answer to the second example as well, but I'm going to suggest that you try it on your own first. So let's look at our first example. It says each dimension of a square deck at the back of a house is increased by 3 meters. Draw a diagram of the situation. Find a simplified algebraic expression for the area of the new deck. Find a simplified algebraic expression for the increase in area. All right, so let's draw a diagram first. So we have a square deck. It doesn't tell us what the dimensions of the deck are, so we can say let x be one of the sides. So our square deck, it's a square, so all the sides are going to be the same, and all the sides are going to be x all the way around. Now when we build a new deck, we're going to increase the sides by 3. So we're going to add 3 to every side to get a larger deck. It's still going to be a square, but all of our sides are just going to now be 3 bigger. And our first question is, give me an algebraic simplified expression for the area of the new deck, this bigger deck. Well, how do you find the area of a square? Well, to find the area of a square, you take the side length and you square it. Or you do length times width, but the length and width are the same. The side length is x plus 3, so we're really just doing x plus 3 squared, which is just x plus 3 times x plus 3, which is really just length times width. So if you'd gone to length times width first, you weren't wrong. And now, if we're doing length times width, we just have to FOIL. X times x gives us x squared. X times 3 gives us 3x. 3 times x gives us 3x. And 3 times 3 gives us 9. If we collect our like terms, we end up with x squared plus 6x plus 9. And there's the area of our big deck. C. Find a simplified expression for the increase in area. That means how much bigger is the deck now? Well, we know how big the big deck is. How small was the original deck? How big was the original deck? We'll call this the area of the small deck. Well, it would still also be side squared, but this time our side length is just x. So our small deck is just x squared. Big, small. We want the difference. So the area would be big minus small. So that would be x squared plus 6x plus 9 minus area of the small, x squared. Well, collect your like terms. X squared minus x squared is 0. So we end up with just 6x plus 9. And that is our final answer. Now, this style of question is a very famous quadratics question to show your work with expanding and collecting like terms. The next example is very similar. The only difference is the shape is a circle instead of a square. And I said I wanted you to try it on your own, but now that I think about it, it's a little tricky because there's pi involved. So maybe we'll work through it together. The radius of a circular helicopter landing pad is increased by 3 meters. Find the simplified expression for the area of the new circle. Well, here's our helicopter landing pad, and the radius was increased by 3. So what's that mean? Well, that means the original helicopter landing pad had a radius, let's call it x, small. And then we made it bigger, and now the radius is x plus 3, big. So same setup as the original question, except we're just working with circles. So first part's find a simplified expression for the area of the new circle. So how do you find the area of a circle? It's pi r squared. And we want for the new circle or the big circle, the radius of our big circle is x plus 3. X plus 3 squared is exactly what we did in the previous question. If we go look, x plus 3 squared gave us x squared plus 6x plus 9. So I'm just going to steal that. I'm not going to do the FOIL again. X squared plus 6x plus 9. And that comes from foiling, and it's just stealing the work from the question we did before. Now, what's different about this question is that we got pi involved. Pi is just a number, so we can just distribute it. Now, the thing is, we don't want to, use 3.14 and work with decimals, so we can just keep pi there as a symbol, and I'll show you what this looks like. Pi times x squared just becomes pi x squared. Pi times 6x just becomes 6 pi x. Pi times 9 just becomes 9 pi. We treat pi as if it's another variable. That way you don't have to use it and work with decimals. So here's our expression for the new circle. We'll call that area big. I should have used n for new. Whatever. Too late now. B, find a simplified expression for the increased area. Same as the last question. To do that, we need to do the area of the big circle, subtract the area of the small circle. That'll give us our difference. Well, we know the area of the big circle. It's pi x squared plus 6 pi x plus 9 pi. What we don't know is the area of the small circle, so let's figure it out. Remember, it's pi r squared. Our small circle is x, so it's pi x squared. And there we have it. Area of the small circle is pi x squared. So we're going to subtract the area of our small circle. We're going to subtract pi x squared. And now, if we look for like terms, look what we've got. We've got pi x squared minus pi x squared. Those are opposites, so they go away. And we end up with a very familiar answer of 6 pi x plus 9 pi. And why is that familiar? Well, it's the same answer as the last question, except we've got pi's involved. All right, that's it for part 2 of lesson 5.2. This is a look at quadratic word problems featuring some expanding of special products. Thanks for watching, and I'll see you in our next lesson, 5.3.